Hello, good morning and welcome to the second day of the Hat celebration. And it is my very great pleasure to introduce another speaker who needs no introduction, especially if you were here at the panel last evening, Professor Chaim Goodman Strauss. And his talk is Questions in Tiling, Open and Closed, even though I think it should be open.
Well,
yeah. Thank you.
Thank you very much. So thank you very much. It's tremendous to be here. Tremendous honor and tremendous event. And thank you. I think we should all again begin the day by perhaps thanking the organizers. So really, genuinely, this is an area that generally doesn't seem to attract a tremendous explosion of interest, certainly not. So that's also very gratifying. So about 25 years ago, I produced a preprint called Open Questions in Tiling, and I'd like to just sort of revisit that and discuss some of the status of those questions and the framework in which these questions are placed. So let me just sort of sketch that out a little bit. So in any given fixed... So I have to describe all of this stuff. Obviously the whole point of the talk is to tell you what all this stuff is about. So in a given fixed, nice enough so-called setting, well, what I mean by setting is just we have to just describe, what space we're working in, what isometries we're working with. So for perhaps some tilings formed by congruent copies of some finite set of shapes in the Euclidean plane. That would be a setting. And by shapes with no markings, perhaps that's another thing that we might specify in a setting. But whatever setting we mean, if it's nice in some sense, which further has to be described, then we have this collection of implications, which I'm going to describe a little bit about today. So there's no real need to go into what these are at the moment. But in any setting, what we might ask are, which of these hold? And so in this, for example, in the sets of tiles in the Euclidean plane, just moved around by just Euclidean transformations, each of these is a fact. So that's the kind of thing that we're talking about. Now I should say that in the paper, it's a little bit, honestly, embarrassing because I made I think I got the questions right, but I got every single answer wrong. So every single conjecture is exactly the opposite of what has turned out. And I'd like to just take a moment to explain that, because I think it's something that I learned over subsequent years and I think is pretty valuable. So when I was first working on this, say this version of this 25 years ago, I still sort of had this kind of naive faith in the tractability of the universe. I really mean that. And then I soon came under the influence of one John Conway. And so this is my name for this, Conway's presumption. This is the only time this has appeared in print, and this is not his words. So he had nicer ways of describing this. This is the most succinct way I could get this down. But basically the upshot is that if you're in a position where you're trying to decide if something's computationally undecidable or not. And so yesterday I described this in just kind of complexity. What I really mean specifically is computationally undecidable. So if you have some sort of combinatorial gadgets, like anything, symbols on a page, tiles, whatever, and they start to behave in intricate ways that are not immediately tractable, that in particular, that there's no tractable behavior sort of emerging, then you might as well just go for it and bet, just simply on not necessarily mathematical or scientific fact, just simply on a betting basis. You should bet on undecidability. That's the presumption. And the reason is pretty simple, is that undecidability is a remarkably low threshold. That's not something that's widely appreciated. The Gödel's theorem, turning into undecidability, computational universality, all of those kinds of things are very close to the surface in any combinatorial setting. They really are. It's something that mathematicians we ignore because we really run from it in some sense, because there's this idea, correctly, that mathematics, at least mathematics as humanly practiced, is elegant, it's tractable, it's describable. Things happen for, when we say things happen for reason, we mean a simple, understandable human reason, not a telephone book size, well, those don't exist anymore, but you know, a telephone book size proof. And so because of that, it's not necessarily, in my view, it doesn't seem to be very widely appreciated that computational universality it doesn't take much to touch it off. On the other hand, so computational universality doesn't take much. It's hard to sometimes prove it to get the gadgets to go. But at the same time, proving something is not computationally universal is so unlikely and difficult in most settings that if you're just simply betting money, bet this way. It's as simple as that. And like, had I realized that, then it turns out that this accurately predicted all of the events of the last 25 years, really. But it's interesting because it's kind of amusing looking at my own sort of progression towards appreciating this. So 25 years ago, I have all these pronouncements like, oh, this is going to be decidable. There's not going to be an aperiodic monotile. And then this sort of slowly absorbs. I was looking back at my various talks and pronouncements, and it's like, it took me several years to really absorb this lesson. I'm still sort of hedging for quite a number of years. But in the end, this seems right, and it did work. And so this is turned out to be valuable in tiling, and maybe will inform us in the future. In any case, for decidability, so for tile, just if we have lots and lots of sets of tiles that we can use to fit together in the form tilings of the plane, all of these things turned out to be true. But just to take another example, whatever these are, we'll describe that. Then for a single tile moved about by translations only, these are all now known to be false, just to give another example. But this is not trivial. There's actually literature behind some of this. In particular, proving that there's no weakly aperiodic protoset, which I'll describe in a bit. But of course, recent work by Rachel Greenfield. Are you here? She'll be speaking this soon, and we'll discuss how, at least if we throw on some extra room, we can get this much. I suppose probably the rest of the thing could be filled in pretty readily. By setting, let me describe that first. So I have to. There's a lot here to unpack. So let's begin. So by setting, here's some examples. We might mean tilings formed by. When I say tilings formed by, what I mean is that we have some set of tiles, which is often called a protoset, from which we can take copies and put them into the plane. And we have to describe several things. We have to describe, first of all, what kinds of things are we putting into the plane? What kinds of things are we copying? Actually, more basically, we have to even describe what geometric universe we're working in. We have to describe the motions that we're allowed to use and any restrictions on the tiles themselves. So this, of course, is the original, sort of the Big Bang definition for our subject. A finite set of squares with colored edges that must match on neighbors. Form with translations only would be the Wang tiles, or congruent copies of a single shape in the hyperbolic plane. This is it doesn't have to be an Euclidean plane. You have to specify our geometry. We might mean, just translated copies of a single unmarked shape in the Euclidean plane, or this is a little bit badly worded, but here we might mean chiral tiling. We have a set of tiles that by orientation I mean left or right orientation. Or we might mean, but see, this gets kind of out of hand very quickly. So one thing we might mean is where we might allow marked edges. Okay, great. Well, what do I mean by marked edges? So we might, I just sort of have this vision of this slide just growing and growing and growing with more and more convoluted subclauses of possibilities for, what can happen. Because really, in fact, a large part of the literature over the last 50 years maybe is just sort of sorting out, just even recognizing that this is important to pay attention to be clear about what our definitions are, and specific, really open and transparent and explicit about what's going on. And so that's also part of what I'll discuss. I should say this talk may be, we'll see how, it might not take that long. Let's find out. So I think we all know this part, and just to remind ourselves how this works. So I don't think I spelled that right, did I? Well, sorry about that. So anyway, Hilbert's Eisenstein, whatever it is. So this is like, it's great because, see, there's this real thing at the bottom of this. You know, this recreational topic that you can explain and play with kids and can explode across the internet, but we can always go back to Hilbert in at least two ways. Because, so this is, I like to use this one. So Hilbert had this program of basically, could we have, a mechanical crank that could sort of sort through formal logic and just even to ask, does a given first order logical formula have a model? Is a big deal. And so even in the 60s, there was still a particular open case of this question. And so Hao Wang was working on that and hit on this idea of using square tiles as sort of representing logical fragments. Because if you think about it, as we'll see in this talk, I mean, really, tiles and any kind of mathematical fragment really kind of have a similar thing. They have to fit together in certain ways. So logical fragments, don't make sense unless they satisfy certain rules about what goes next to what. And that's really literally what he had in mind, at least as I understand it. So he asked, given a set of tiles, can copies of these be used to form a complete tiling of the entire plane? Of course, that's not really what he asked because he was interested in a specific setting, so we have to begin to be a little bit more precise. He was interested in square tiles with colored edges that must match on their neighbors, and then we only allow shifts. No, that didn't turn out to be terribly important, that distinction, but just to be clear. And so that was the domino problem. The domino problem asks, okay, if you have a set of tiles, can you use them to form a complete tiling of the entire plane? Just to put this in context, the completion problem, which has been mentioned a couple of times, is fairly transparently not undecidable. So the completion problem asks if, given a set of tiles, and you specify that some particular tile has to be placed, or if you prefer, some configuration has to appear, or various other ways of stating this, then can a tiling be completed from that starting seed or that starting configuration? And the idea is pretty simple. You want to just emulate an arbitrary Turing machine. So if you don't, I'm presuming there's some knowledge of this, but just to state it, so Turing gave this very simple model of computation that's remarkably powerful. It can do basically anything, which is, at least so far as we understand from the Church-Turing thesis, which is essentially an axiom that this is as powerful as anything we might want. And so here there's some very simple instructions. I think almost certainly most of you are aware, but just to go through it. So here we have a little transition table, and it just says that if I'm reading so at every moment we have a read-write head that's going up and down a tape, and we're in a given state, and then we're reading a certain symbol. And so if I'm in state A, reading a 0, I'd write a 0 on the tape, move right, and go into state B. Simple as that. And then we can make a little movie of how the Turing machine would move around over time. So we have a little movie that describes exactly what the state of the machine is, and you can just kind of crank this along forever or until it stops. And the point is that just as with logical fragments, this obeys certain rules. You just at a glance, you can, not at a glance, but locally at a glance, you can tell if this alleged picture on the right really really faithfully describes the rules on the left. You just simply look in any given region. Okay, no, there's no read-write head here, so that's okay. 0 is above 0. If it was 0 above 1, I know there's a problem. Or in this little zone here, I see this is faithfully recording that I'm in state A reading a 0, and sure enough, I have a 0 there, and I've gone into state B. So this is the kind of thing you can just tell by sort of looking at the picture. And so we can turn that into a collection of tiles, which is basically that picture chopped up into squares. And And then, so given an arbitrary Turing machine, we can't tell if the machine halts. Therefore, we can't tell if we can. So halting, if the machine ever halts, then this construction would crash and we wouldn't be able to complete the tiling. But there is a trick here, which is that we must have this start configuration to get the whole machine moving. Without this little guy is what sort of triggers this whole cascade of other tiles. And as stated, without that, see, we can certainly, with this collection of tiles certainly admits a tiling, namely the dumbest possible one, which is just blank squares. So the mystery is, how do you get the computation started? So, okay, so with any nice setting, we can ask whether or not a given set of tiles admits a tiling, and I think we know, we've discussed this before, so there's an obvious algorithm to tell whether or not a set of tiles doesn't admit a tiling. You just simply enumerate larger and larger patches, and by that I mean you're covering larger and larger, completely covering larger and larger disks. And this is somewhat non-trivial. This is the famous theorem with the snappy name of Theorem 3.71 in Grumman and Shepard. Craig referred to this yesterday. What's that?
Or it's a mistake. That was the wrong theorem.
It's 8.1, isn't it?
No, so 3.7.1 was 1D implies 2D.
Oh, yeah.
Yeah, that was my mistake yesterday.
But there's one, it's like that. It's something like that.
Yeah,
so the extension, oh, it does have a name.
Yeah, it
It
does,
does have a name. Right, thank you.
Yeah.
So in any case, but it's somewhat non-trivial, even though it might seem otherwise. So if tiles can form patches covering disks of arbitrary radius, then they can cover the entire plane. So conversely, if you can't cover the entire plane, then you have some size disk that won't be covered, and you'll be able to enumerate them. However, of course, there's another little assumption tucked in here, which is that there's only finitely many configurations of a given size, patches of a given size. And so this algorithm halts no if there's not a tiling of the plane. And we can also discover if it admits a periodic tiling by enumerating larger and larger patches in the same way, and then as we go, just checking to see, do I have a finite patch that can be used periodically? And Wang gave this, so no, I'm in good company at least with my overly naive conjectures, because Wang made the same kind of mistake. So he gives this fundamental conjecture that basically this is not going to happen. Solve a finite collection of tiles, admits a tiling. Basically, I'm just translating if and only if there exists some fundamental domain that, in other words, a set of tiles admits a tiling if and only if it has a periodic tiling, basically. And then, if that's true, then we have a decision, an algorithm for the decision problem. That's essentially what he's saying. So, if the fundamental conjecture were true, we would have a decidable domino problem. And then he's reasonably, I suppose, suppose that what we would call an aperiodic set of tiles could exist, and obviously he was wrong. And I think this history's been covered pretty thoroughly here. But within a few years, Berger proved the domino problem is undecidable and gave the first aperiodic set of tiles, and so we had this. I'd like to just sketch the proof because I think it came up yesterday, and it would be nice to just see it. So the idea basically is, how do you get the seed tile started? How do you get the computation going? And the idea is that you simulate the machine on larger and larger domains. So you have like some domains where you run it for, like, say, 3 steps, and some for so many steps, and so many for so many steps. And if the machine never halts, you can do this on arbitrary large domains. And if the machine does halt, there's some size domain that it crashes. Well, now the only question is, how do you get all these different size things into the plane? And this is where the hierarchical structure is. I won't explain how this really works in any more detail than this. But basically, with the supertile structures, you can kind of attenuate the machine. So this is the same kind of picture I had before. It's just now stretched out over this kind of weird domain. The only thing that's really happening is that these gray squares here, which are the original gray squares of the picture I just showed you. And everything else is just sort of stretched out, sort of attenuated across that. And so this gives you room that to fit in sort of some smaller domains within where you can run the smaller simulations. And this in turn can fit within, sort of cozily within larger domains where you can run larger runs of the machine. Obviously there's a lot of details, but that's the essential idea. And in particular, that explains how you can get these seed tiles everywhere, because the hierarchical structure, as you've seen, all of these substitution tilings basically really do look the same anywhere you look. And in particular, anywhere you look, you have plenty of opportunities to get that computation started. So that's the key idea there. And that was used profitably in many others. So, as Berger's example was famously complicated, and then we soon had very quickly some very nice examples. What I just showed you was really from Robinson's paper of 1971, where he had an aperiodic set of 6 tiles on which he was hanging that construction. So that was great. But we still might ask, how complex can the behavior of a single tile be? And I really like being here in England because I can spell that correctly, which is nice. Somehow that is the way to spell it. So I have to explain that. I lived here when I was 6 or 7 or something, and so that's how I actually learned how to spell. I don't know why. It just caught my attention. What's that?
I saw neighbour earlier.
Neighbor. Oh, did I write neighbor? Which way did I write it? Did I write it English or American? Oh, that's interesting. That confused me until I was an adult, actually. So, and gray was another one that. So anyway, we must be careful to specify the setting in order to make sense of the question. And this, again, was something that took a long time to sort out. And we are still seeing the effects of that today. So let me just discuss this. So a single shingle may be aperiodic. This came up yesterday in the context of Petra Gommel's example and John and Steinhardt. But also, Marjorie, you mentioned this to me. I don't know what the source of this is. But this, and I'm not, I hope it's right. Actually, now I'm not sure I checked it. But that if you have a single kite, and that you allow it to overlap, then it will but in the wrong way, sort of not by the substitution rule way, but in sort of the wrong way where it overlaps, then this is an aperiodic shingle just by itself. At least that could use, do you remember telling me there?
I remember vaguely. I've been looking through my notes to try to find it the past 6 months. I can't.
Okay. Well, anyway, I'm not even sure I can confidently say that I've checked that. I mean, it's been a long time for myself as well, but that kind of thing definitely does happen, and this is an incredibly elegant example, and surprising, really. So if we allow things to overlap, sure. Or we have Taylor and Sokolar's wonderful example from 2012, right? That's the wrong date, possibly. In any case, the tile is not connected, or maybe we mean the rules aren't next door neighbor to neighbor. Definitely American there. Or the tiles are in 2 layers. There's different ways to get around the problem with this tile. The problem is that this tile, like this thing, has to be pointing in the same way as that thing. And there's all kinds of solutions to this, but none of them seem to be ways to do it with a simple unmarked polygon. And so the rules matter. The rules that allow us the rules for our rules, in a sense, matter. We can, and it's worth noting that we can always trade off complexity in the tiles with complexity in the rules. And so a very extreme example of this is that with even a 2x1 rectangle as an aperiodic monotile, if we allow complicated rules. And the complicated rule here is just an atlas. So we start off with our favorite aperiodic set of Wang tiles, and then we just pixelate. This is a picture. This is literally pixels on the screen. So we just blow that up, and we look at it really closely. And the black pixels we split one way, and the white pixels we split another way. And then we just proclaim that that's an atlas. So every an atlas of allowed configurations. And so any given 2x1 rectangle has to appear uniquely in one of these patterns. In effect, we're just saying that this has to recreate that. So that's a really stupid example, but it really points out that we can't just say, oh well, the rules, we just shove all the complexity of the rules and call it a day. On the other hand, here we have an example by Aman which really illustrates this, which is how many tiles are there here and what are the rules? So if we have the two tiles that are sort of obviously highlighted, the square and the rhombus, then the rules are kind of complicated. The rules are that we have to have these arrows and these little guys. And that's not so, that's a complicated rule. Or we can think of these as unadorned shapes that just have to fit together, and then we have 3 tiles or 4. We have the the arrow actually as a tile, and then cut out of and then these little half moons cut out as well as a tile, and then these sort of weird pale green shapes or whatever's left over as a tile themselves. So you see, here's an explicit example where it's not even really clear how to count the complexity of this thing. How many tiles is that? How many rules is there? And so, I think it's fair to say it's 2 with complicated rules. Or maybe it's 3 with simple rules. I don't know. And here we see a terrific example from Walton and Whitaker recently. And here I think we see, here we really see this kind of push to an extreme where the rules are not like, there are sort of logical rules here, but they're not terribly complicated. So we have a single tile with, it's kind of like on that spectrum of going from here to here. You've pushed the complexity of the rules way down, but it's still, there's some complexity there. Another sort of thing that emerged, this was referred to yesterday, and the way that I would present this hasn't been said yet, so I'd like to talk about this a bit. The Schmidt-Conway-Donzer biprism, and the original construction by Schmidt a few years earlier, has this feature that, it forms these sheets, and these sheets are turned by an irrational angle. And it actually emits uncountably many tilings because of the way the sheets can be on top of each other. You have a sequence of choices. But of those, countably many have a screw axis. And so that's sort of very unsatisfying in some sense. It's definitely not got a compact fundamental domain. There's no finite region of chunk of tiles that can be replicated to form a tiling of space. But something was wrong, and this took several years here. Here's another example that was known in a lot of ways, in a lot of variations. Oh no, where is it? Hang on. Oh, it's gone. Well, here's a picture of it. So as it happens, thank goodness. So here's an example of here's something in the hyperbolic plane. This is one time I went. If you forget the little jigsaw puzzles things, one time I went to a talk and it was like. One time I was at a conference and it's like the whole day everybody was showing a picture of this binary tiling, but in completely different contexts. It was the weirdest thing. Because, of course, this picture can represent many, many different things. For example, a slice of a sheet in the Bob-Stock solitaire, for those of you know what that is. So anyway, here is in the upper half plane model where one of the congruences in the upper half plane model is similarities that have a fixed point on the real axis. So this tile is the same as this tile is the same as this tile, and so on. And we can certainly see that this is never going to have a finite chunk that can be repeated to form a tiling of the entire plane, because every tile has one in and 2 outs. And so if you had a finite chunk that could be repeated, on the boundary you would have the same number of ins as the same number of outs. But if you just think about it, that's not going to work out because you have twice as many ins as outs in a given region. So, but this also admits uncountably many tilings, but it also, countably many of them, you just arrange to have an axis of some kind, and so this thing has a periodic, has a tiling that has an infinite cyclic symmetry. That's to say, you just simply shrink on that fixed point, and the tiling. So again, it's sort of unsatisfying in the same manner as Schmidt's tile. And so I don't know what happened there, but fortunately, so I don't think that's right. Wait, this is the wrong talk. No. Wait a second here. Maybe what happened was this just got inserted somewhere. Okay, never mind. This is the tile. Okay, I think that's what happened. So here we are. So then I should also, so this is what I was looking for. So that this tiling does admit tilings with an infinite cyclic symmetry. And in fact, this construction is almost generic. It really is. So in a very wide class of spaces, we have these kinds of tilings where we have infinite cyclic actions. Huge, but no finite fundamental domain. That's a really very generic kind of situation. In fact, it turns out that just to take triangles in the hyperbolic plane, almost every single, like literally, measure one of the triangles that emit tilings of the hyperbolic plane have this property, that they have emit tilings with no finite fundamental domain, and yet do it also emit tilings where there's an infinite cyclic action. So this was something that clearly had to be sorted out. And so we distinguish weakly from strongly aperiodic. So weakly aperiodic, I guess I introduced, I suppose, because in reaction, strongly aperiodic appeared, Shahar Moses introduced the term strongly aperiodic a few years earlier. And so naturally, weakly is the counterpoint to that. So strongly aperiodic admits tiling without any kind of translational action or screw action or just rule it out, no symmetry of that kind. And then weakly, if we just simply rule out having finite chunks, finite fundamental domains. And so naturally, if you look at the proof of the domino problem being undecidable, it's not that it implies that there exists a strongly aperiodic tiles. It's rather that this being undecidable would imply that there's a weakly aperiodic set of tiles, so that we're not able to enumerate, we're not able to guarantee that we would find a finite chunk that would be repeated. But it does leave the possibility of, so we really have, but it clearly strongly implies weakly, so we have this little bit of the chart. And in the Euclidean plane, however, one reason that this wasn't really noticed for a while is that in the Euclidean plane it just doesn't matter. So maybe this is theorem 3.71. That if you have a period, if you have a tiling that set of tiles that emits a period in one direction, then it'll emit in plane only. Well, plane and some other places. Then it'll also emit a tiling with compact fundamental domain. So in the plane alone, or in the plane, it's sort of a rare place, but then we have this direction here. And we can basically ignore this. So all of these can be legitimately called aperiodic monotiles, but we have to be careful. So in particular, we have to specify the space that we're in, clearly, the motions which we can use to move things about, and we saw with the spectre, do we allow reflections or not? And I'd like to just maybe take a moment to say something. With the spectre, so our position, which I think is well backed up, is that in the tiling literature and mathematics in general that, we are considering congruences in general, but we could argue about it. So suppose we do argue about it, then if we're ruling out, we face this kind of funny problem with the spectre, because the original spectre, the polygonal spectre, we could see if we're ruling out, if it's not legitimate to include reflections, then we could just by fiat say, let's not include reflections with that polygonal tile. And then we wouldn't have to modify it, and it would be a Carlo tile. And that would be fine in the mathematics literature. I think that would have sunk like a stone on Twitter, or whatever, because so it's good that we could modify the edges and just sort of rule it out in another way. And then as we've seen, any further conditions on the tiles and matching rules. And a lot of the games that I personally played have been to sort of fool around with, weird matching rules. and sort of toying with that. But we have to be explicit. So, for example, I think a single unmarked shape is very clean. That's a very clean standard, and one we can't really argue with, I hope. So, okay, so let me just explore a little bit more of this chart. So the H number has come up, and this describes the complexity of tiles that do not admit tiling. So we want to ask, how complicated can things be? And the basically, this is the status for a single. Hang on, this got out of way. Just ignore the bottom, I guess. Okay, so in general, we have this situation that if the domino problem is undecidable, then there has to be a bound on the H number. The H number is how many rings can you extend out before running out of possibilities with that set of tiles, if you have a set of tiles that doesn't tile a problem. And if the domino problem, if this were bounded, then you have an algorithm for deciding the domino problem. You just enumerate out to that bound, and if you pass that bound, you're home free. And so you know the tile's the point. So we have contrapositively, we have this implies that. Just please ignore the bottom. So we have, for a single unmarked shape, this is sort of the history. And I didn't realize Anne Fontaine was, until I was looking at this. I'd forgotten. So the next time I see Anne, I'll have to congratulate her 30 years late or something. And then H, I'm not sure of the name. Amon came up with a H number 3 example, and I'm not sure of the date. And then Casey Mann came up with 5, and then very recently we have this wonderful result with 6. So we don't know in general. So now we have for a single tile, we have the bottom. This part. So we don't know this. This is an open question. We don't know this. This is an open question. This they've resolved. So this is, of course, the Hat tile and the Spectre, very new result. But this is quite possibly, this is amazing to think about. So I have to say, this is like that same tension I was describing. I can't really fathom what a single tile that would be computationally universal would look like, or be, or could exist. But I'm forced to, by Conway's presumption, to just, okay, let's bet on it. Let's bet that's yes. And let's bet that that's yes.
So I
Yeah.
don't understand what the monotile domino problem is.
Oh, thank you very much. So in the context, thank you, in the context of a single unmarked shape of tile, so that's the context, then we ask, is the domino problem undecidable? So we might as well call that the monotile domino problem. If the input is a single tile, and the decision question is, does it admit a tiling? And thank you for, I'm rushing a little bit, similarly, the isohedral number is the complexity of periodic tilers, and we might ask, what's the isohedral number? It's this of a given monotile, or a given set of tiles in general, but a given monotile would be the size of the smallest fundamental domain it can admit. And so again, this has 4 distinct translational. No, it doesn't. But it has. Now I'm really baffled by this. I'm not going to try. But anyway, it has some number. It has isohedral number 2 for sure. So 2 different orbits, 2 different kind of ways, aspects in which the tiles are in the tiling. And so Jarkko, I don't remember what year this is, but I'd forgotten completely about this until I was preparing for this talk. But Carrie came up with a number of these isohedral number examples. And you have to remember that this is like the state of the art, basically, and just 25 years ago, was this isohedral number 4 example. It's 4 because you can flip it's not 8 because you have, you can rotate 180 degrees. And then soon after we have this incredible example by Joseph Myers of isohedral number 9, and this one by 10, which is the current record. And indeed, I was carrying wooden copies of these around, as Craig mentioned yesterday, because this is incredible. This is absolutely incredible. This is definitely when I started to feel, okay, really, I got this. We should start betting on complexity, because what in the world is going on here? And one of the questions, Joseph did these, by the way, Joseph also did these massive, massive searches that have been since extended, and this is it. So this raises some other questions. Is there a fundamental barrier to the complexity of a single tile? Is this really it? Or, as somehow seems maybe more plausible, is it just simply that these are becoming asymptotically rarer and rarer, and that we would expect to see that if we can, maybe every 3 orders of magnitude, like every time we add 3 more zeros to the search, maybe we'll pick up another interesting example. Or maybe not. That's, we don't, who knows? So, in any case, this is related, as I had forgotten, Jarkko also pointed this out to me back 25 years ago. Whether or not we can ask the period problem is whether a given set of tiles admits a periodic tiling. Now that's just basically the flip side of the domino problem. It's that if you have no aperiodic set of tiles, you will also be able to determine if the tiling has a periodic tiling, because you just again enumerate and you either find a periodic tiling or you find it doesn't tile at all. And so, in particular, the period problem. This is the relationship with isohedral number. The period problem is decidable if the isohedral number is bounded. And so we have this little bit. And again, for single tiles in the plane, we don't know if the period problem is decidable or not. We don't know if the isohedral number is bounded, and we don't know, and we do know now though that there exists an aperiodic monotile. So just to give you a quick rundown on some other stuff, in the hyperbolic plane, the situation in 2000, say, was this. It's not necessarily trivial. So the completion problem is undecidable. That's because basically we can run the same kind of construction in the plane, but we can sort of attenuate it across. It's like just the white squares are doing the simulation that we had in the Euclidean plane, and the gray squares are just kind of managing filling it in. But notice that the distances from square to square are growing exponentially on each layer. So it wasn't really clear how to possibly distribute those seed tiles to get anything done. So anyway, we do have some results. So by 2005, I had produced a strongly aperiodic protoset. Essentially, it's not very cleanly obvious, but it is essentially Jarkko Kari's novel construction of aperiodic sets in the plane extended into hyperbolic space with some kludgy, unnecessary modifications, which now, that's how it is. And then in 2009, another construction sort of modifying Robinson's in the hyperbolic plane. We have the decidability of the domino problem was resolved. I'm sorry I don't remember the dates, but in the later half of the 2000s. What? 8. And Morgenstern right around the same time with a very nice, Kari's proof is very nice. It's since been modified in a number of ways in other spaces. And then we have no computable bound on H number. No bound, let's just say, on H number was from Sokolar around 2006. I'm sorry, I ran out of time to track down the dates. And just so that's sort of where things... So that's pretty cool. So now there's just a little bit more to do. I think this isn't really because this is hard. I think it's just that nobody bothered, perhaps, that the period problem and isohedral number. Meanwhile, there's a huge literature in somewhere in geometric group theory. So I'm assuming that this is a pretty broad mathematical audience. I'm just sort of speaking a little bit to specialists. But geometric group theory is basically a way of... Well, I'm not even going to try. But the basic point is that Wang tiles are essentially square tiles that are fitted together in a plane, and there's this particular set of motions that we can move them around. It's basically the integers cross the integers. and Z cross Z we would call it. And that's what we call a mathematical group. It has a particular graph. We can obviously just draw, sort of connect the centers of each tile and make a square grid. And then we just translate this into this other language called subshifts of finite type, which I'm not going to bother explaining. And we just basically translate everything over. So the question of does a given set of tiles emit a tiling is now called does a given definition for a subshift actually define a non-empty subshift. I'm not going to explain that, but some of you might know. And then we play this game, and we get that this is exactly the same business as before. There's a weakly aperiodic subshift of finite type. That's the spell checker that put that there. That's there. And then the non-emptiness problem, this is just the domino problem in another form, is undecidable, and this is the same thing. And as a strongly aperiodic set of tiles. And this is really a pretty, there's been a lot of activity in the last 10 or so years, and this is, again, for experts in that, these are quasi-isometry invariants, so this is sort of something about the overall shape of the overall large-scale shape of these structures. The large-scale shape of these spaces determine the answers to these questions, not the space itself in a sense. So with many of these things have sort of, in a certain sense, have places on which you can run Berger's construction, these Z cross Z subgroups. But just to give you some recent news, I think, we have a strongly aperiodic subshift in all, I put word hyperbolic in here because to emphasize, if I'd said hyperbolic groups, everybody would think the hyperbolic plane. I'm just emphasizing that this is in a much more rare, much more abstract setting, much more general setting, and there was a lot of work to get this to work. But then, just this spring, and honestly, to be honest with you, this really pissed me off because I really wanted this result. I was really aching for this. And then what made it even worse was that we missed, it's just like we made a little tiny wrong turn, which really, and then this one here. So I think I'm being told to stand, you can just read that on your own. Take a quick screenshot, and that's it for me. So thank you very much.
Thank you very much for this very enlightening tour de force of the state.
Mm-hmm.
The state of the Wang and decidability related problems over the past 50 or so years.
Yes, thank you.
Wow. Thank you. I think we've got time for one or two quick questions. If anyone has
I gave you all these questions. I guess we're exhausted the possible.
Yes.
Yes, I want to know something. I'm curious your opinion on the extent to which these problems are accurately, whether solving or attempting to solve these problems on the limited domain of polyforms, like simpler classes of shapes, will inform the full solution.
The full solution of what?
Of some of these problems. Like, for example, can we investigate the larger question of limits on H numbers? Can we get everything we need to know about that by studying the problem on just polyominoes or just?
So I've already made a fool of myself once on this whole score. So I'm not gonna speculate too closely, but I mean I think at this point, right? We have obviously it's all bets are off, right? I mean in terms of any kind of pronouncement that there are limitations on the complexity of these things without any just right now without further insights it just seems foolish. I guess I would be forced to say that I would if I have to choose a bet, I would bet on the complexity of the situation and say, yeah, that probably polyforms are fine. But honestly, do I really believe it on some level? I don't know. I mean, Christ, it's like, how hard could it be, man? But I don't know.
Thank you
Thank you very much.
Yeah, and I'd like to